Okay, welcome to Lecture 4 of Compliant Mechanism Design. Today we're going to be jumping into the fun stuff, and it's just all fun from here on out, so I'm glad you survived Lecture 2 and 3. We'll start by just talking about design theories, and we're really going to talk about 3 design theories. The first 2 we're going to kind of gloss over. Second one we're going to go in, or third one we're going to go into pretty good detail, and that's the reason we're doing that is because that's leading up to the main theory of this course, which I think is the most powerful one. So, okay, so here we go. Topology optimization. Well, honestly, the first 2 are also extremely powerful. The last one's just different. So, topology optimization is super good to know about. Okay, it's a computational approach. Okay, there's many different formulations for topology optimization, but let me give you the idea of it. Okay, so one formulation is you have all these nodes in some kind of grid, and you connect them all by beams of different lengths. You know, you connect them all up like a big web of beams. And you then say, okay, my compliant mechanism lies somewhere in that mess of beams. And so you specify the functional requirements. You tell the computer, okay, I want to ground all the nodes or all the beams on this side. And what I want is some input here. When I pull that, I want this node to go down some transmission ratio. Say when I pull this 1, this goes 3 or something like that, right? So you specify what you want, and you set everything up in the computer, and then you hit go. And what happens is the computer will remove a beam, and if it helps, if by doing that it helps do this a little bit more, the thing you want, given these conditions, then you leave it out. If it hurts, then you put it back in, and you just keep doing this. And it's kind of a evolutionary approach. They call it a genetic algorithm. So you can see here's, it just kind of starts taking things away if you watched it until it kind of crawls to a local minima, optimized design that does what you want. Now, this design shown here is, they also set it up to be symmetric about this line. So this would be flipped, and this was an actual thing that Sri Dakota made here, and you can see the final resulting beam. So it's pretty cool. They call it a genetic algorithm, and because it's basically doing what genes do. This is what how evolution works. There's a random mutation, and if it hurts, you die. If it helps, you live and pass on your genes. So, and then through many generations, many iterations, you crawl toward something that works. Not necessarily an optimum, but something that helps you survive. So, this is the same way. You can get to these designs that end up, because they're kind of mimic nature's way of creating things. They look very organic, very natural, very non-intuitive. It would be tough to have someone intuit where to put all the beams and to put the right angles and everything. It ends up, looking kind of like bone, to be honest, and sinews and interesting things that formations that nature makes. Topology optimization is designed, so they're very non-intuitive and interesting. Okay, so but anyway, that's one way to do it. That's the beam within a lattice kind of approach. Okay, another way to do it. Oh, and by the way, this was designed to be a gripper. You grab here with your hands and pull this back, and this clamps together. So that's what they're doing there. So another approach comes from this video. I mean, this is just one of many videos on YouTube. Right. So what it does is it starts with some kind of random pattern of mass. In this case, the blue is the mass. And for whatever given constraints they have, it starts taking pockets of mass away. And again, if it helps, you keep taking away. If it hurts, you put it back in. And you just kind of iterate genetically over these things. This is for a higher complexity factor. And so, the design can end up looking fairly different, the output of the design, depending on, one, how you start and what your initial conditions are, and how much instructions you give the computer. So it's real art to set it up, but then you just let it go, and it designs its thing. So you can do this with multi-material. You could put splatterings of different mass in there, and then just go and see if it adds the different material properties in different places. And and it can generate some very non-intuitive designs that no one could ever think up. Okay, and this is a bona fide design approach. I mean, this literally, I mean, you don't know what, it's blank sheet to final design, and the computer just kind of does it for you. So it's a very clever thing, a very powerful theory. You know, there's some strengths and some limitations, okay? And even though, you know, these are kind of old a little bit, so I'm going to update these as I talk, but, you know, it's got a lot more strengths than it has limitations, and all these limitations can be overcome, okay? So topology optimization is a very powerful thing. It can generate optimal, like I've said, very non-intuitive designs, things that designers could never really think of or would, you know, would never come across without this approach, or allowing nature to kind of, you know, in an evolutionary way, create them. And so it can come up with some very interesting designs. One of the problems is that a lot of the designs that are generated end up not being very practical to implement. You know, like we like, you know, 90-degree angles and nice features that can easily be fabricated and are clean and geometric and everything. So when topology optimization generates these very organic, you know, bizarre-looking structures, they're kind of difficult to implement in real practical machines. And sometimes the approach generates things that are beyond what, I mean, you know, it's tough to teach the computer common sense. Like, you know, sometimes it'll find designs that have super impossibly thin features, or floating islands of material that could never actually exist in reality. So, you know, it's really like when humans design stuff, they take for granted their common sense. They know what they're going to make it, what approach they're going to have to make it, what material they're going to make it out of, and kind of they know a lot more than they consciously realize when they're designing things. And the computer literally has no common sense or conscience, so it only does what you teach it. And the tricky thing is if you put too many constraints, if you try and teach the computer your common sense, and put in too many principles, then it's very likely it won't settle on any meaningful solution. So it'll settle. Not many people use this for precision applications, you know, the really high precise guiding light and optical mounts and these kind of things. It's tough to teach the computer precision principles, like, you know, thermal stability, and you know, we need to cut this with a wire EDM, and so, you know, you have to follow the rules of wire EDM, and it needs to be exactly constrained, and you know, all these principles. I mean, I'm going to teach you what exact constraint is today, but there's all sorts of principles that if you teach the computer, as well as you don't let it get features too small or floating islands and all these things, it starts becoming computationally very expensive and burdensome, and it can't find a solution. So, but you know, this is a very active area of research, and a lot of people are coming up with solutions and teaching it common sense and finding clever algorithms to actually find a solution. So none of these limitations are not overcomable, okay? I could see the day where they could generate some very clean, geometric-looking precision system designs with a lot more code advancement in the algorithm. So generally, it generates 2D mechanisms with translations. You know, the nodes translate with certain ways, but you know, the only reason for that is it can become computationally intense to do things 3D. People certainly have done things in 3D. You just have a three-dimensional space and 2D plane, and you take your mass away in 3D. It just adds immense computational complexity and can really slow things down. But as computers become more and more powerful, that's not the biggest deal. So they can do 3D, and they can do any motion. You just have to be clever in how you set it up. And then one downside is that, you know, it doesn't leverage the common sense of the user. You know, it's very difficult to imagine the day when the computer will have better common sense than an experienced engineer. I mean, possibly that could come, but you know, you'd almost want during the design process the user having some input, say in what is being designed. And right now, all their input is at the beginning, how they set up, what they teach the computer. When they hit go, they're no longer in the equation. The computer just goes down whatever path it goes down and generates a design. and it would be nice if the user could have some more say during the design process. Right now, that's not possible. And so, anyway, you see this last one. These have overlapping beams, and the beams cut out here and everything. So it's like it didn't take into account how to fabricate it, and this obviously needed to be 3D printed to even be feasible to make. But again, as 3D printing gets better and better, you don't really need to worry about whether it's can be made with planar approaches and assembled, and these kind of design, for fabrication considerations are kind of going away. So anyway, I'm a big fan of topology optimization. Very powerful. It's getting more and more powerful every day. You can look up, there's companies that sell software tools of this, and if you're really designing compliant mechanisms seriously, you can generate very interesting designs using this, so it'd be worth looking into those software packages and getting them. And sometimes there's applications where topology optimization is really the only way to do it if things get very complex, okay? And you just rely on the computer to find something. So anyway, here's one of many reads you could do to learn more about it. Okay, so that's approach number one. Okay, approach number two is also it uses math, but it's not it's not like the computer designs it. It's a little bit of an art. It's called Pseudo-rigid Body Model. PRBM you'll look it up and see that's the acronym used for it. Okay, this was developed really by Larry Howell. He did it at Purdue with Ashok Mehta, but really it took off after he went to BYU. But the idea is. Remember, it's very difficult, if you're going to deform a beam, depending on what material it's made of, depending on its geometry, depending on how thick, thin, long it is, and everything, depending on how you push on it, where you push on it. Imagine this is a force, but its y component is p, and its x component is pn. So you can just tune n to tune the angle of that and everything. Depending on all these complex things, it's very difficult to track how this point would move as you load it for a given force, and because it's a very nonlinear problem. So what Larry Howell did is when he developed pseudo-rigid body model, he said, well, let's make a pseudo-rigid body model. let's model this as if it were a rigid link kind of thing, and see if we can create a model that mimics this to describe it, to simplify things. So it's like, okay, say you wanted to know what A and B were for a given n here, given force and direction. What he found is he said, well, look, for this specific example of a cantilever, this point can be traced and identified if we model this as if it was a rigid bar here, or rigid bar here with a pin joint there. So it essentially rotates about this central point, okay? For the first order approximation, it's not exact, but he said it's pretty darn close. You can track how this moves if you model it like this with a pin joint there, with this at this specific location, right? So he said, like, if n, he came up with these models of n. If n is 0, in other words, if the force is pushing just straight up, then this factor here ends up being 0.85, so it's 85% of the length of the flexure is where you put this. It's not at all obvious where you put it, even if having a pin joint in this rigid system mimics this. The question is, where do you put the pin joint? Well, he found if n is 0, you put it at 85% the length, and then that'll capture the kinematics, the motion, the path it takes. But then how do you capture the elastomechanics, the stiffness of it? Well, he puts torsional joints there, and it says, this will approximately be the same kind of torsional stiffness as the beam would exhibit according to this equation, which, his derivations are in the, he wrote the textbook on compliant mechanisms, and a lot of that talks about pseudo-rigid body model and how he derived these things and how he came up with these models, okay? But, so the idea, again, is you take some complex, nonlinear, very intense compliant system, and you can simplify it to come up with a rigid body analog that kind of moves similar for government work, right, first order approximations that gets you in the ballpark and kind of matches the stiffness, and then you're able to analyze it much more simply, right? And he comes up with these models and these equations to find out where you put them and what the stiffness is. So, and the model has to be kind of different for different scenarios. You can imagine for like a 4-bar, it's no longer just a cantilever, it's 2 flexures and everything. And he came up with the equation for, okay, this is like a traditional rigid 4-bar where the pins are a certain distance down and these are certain lengths. And then these guys have, torsional springs have certain stiffnesses that mimic these. And if you go to his website, he has Lego models where you can actually build these and put them on top of the compliant versions and see that they do indeed follow the exact same path and course. And with the torsional joints, they feel the same. They provide the same resistance and have the same stiffness and everything. So there's a lot of papers on pseudo-rigid body models. People are always coming up with these models, these kind of building block things, so that you can, take a rigid, analog and convert it into a flexure, form, or vice versa. So you can go back and forth. You could either take this flexure system and then use pseudo-rigid body model to see, okay, well, where do the joints have to be and what do the torsional springs have to be, or you can go from this to that. And so that allows you to both analyze and design things, okay? So here's how he went from, this rigid thing to this very famous compliant thing, right? And so basically what you do if you're designing is, this is such a powerful approach because remember, I told you the reason people shied away from compliant mechanisms is because they're a lot harder to design. It's just much easier to plan paths for things, rigid links that you can assume never deform, never bend, or infinitely rigid, and yet have these joints with very well-defined guided motions, and it's very clear to know what their axes of rotation are and the directions of translation, and then you can work out all the math. The math becomes much more simple to design things that move the way you want with rigid mechanisms. And so what Larry did is he basically said, well, let's use hundreds of years of this mechanism theory for rigid mechanisms, allow designers to design things with rigid mechanisms that move the way they want, and then allow them to put the torsional joints where they want to have the stiffness they want, but then convert that into a compliant form using pseudo-rigid body models, so you have a fully compliant mechanism that essentially does the same thing. Okay? So that's a way to simplify things. Instead of just rushing into the complexity of dealing with all these nonlinearities and this intensity, what we do is we design a rigid linkage system first, and then we convert it to its compliant guy using pseudo-rigid body models. Okay? And again, if you want to analyze it, you go the other way. You take the thing, you convert it into a rigid mechanism with torsional joints, and then you analyze how it moves and what its stiffness would be. Okay, so it's an awesome approach for designing and analyzing large deformation compliant mechanisms. Okay, it does take some familiarity with the approach. It does take some understanding of the models, which could be a downside because with topology optimization, there is an art to setting it up, but largely once it's set up, it's just like you're like a monkey banging on a machine. You just turn it on and it does the work for you. In this case, you need to be fairly skilled in the art of knowing your pseudo-rigid body models and knowing how to apply them to analyze or design these systems. But once you know a couple simple ones, you're able to do this fairly simply and get compliant mechanisms that can do large deformation motion paths that you want fairly accurately. And so it's a really nice approach if you just want to design standard compliant mechanisms that deform large amounts. Okay. Again, it's not terribly suited for precision applications, things where you want things to move just tiny bits, maybe for a microscopy stage or moving an optical mount or something where you want really high precision and accuracy. You're moving things tiny amounts. Because remember, pseudo-rigid body model it's only approximate. It doesn't these pseudo-rigid body models don't absolutely nail the entire motion path of the compliant mechanism. It just gets you in a very close ballpark. And when you're doing precision things, you want to be exact. Okay, so not so good for that. It is more a tool for analysis than design. It's a little trickier to design. It takes some real skill. And then they're generally, it's limited to what models exist. And again, it's an active area of research. People are publishing papers on different models for different scenarios. The problem becomes dramatically more difficult in 3 dimensions because you can imagine things can deform in a whole 3rd dimension. And the models are much more complex and difficult to use and there hasn't been too much research in that area, but people are trying to extend pseudo-rigid body model to 3D spatial mechanisms. Okay, so the best book to read on this is Compliant Mechanisms. There's also a handbook of compliant mechanisms, both by Larry Howell. And pseudo-rigid body model is great. Okay. Oh, the other thing is the designs, of course, that are generated pseudo-rigid body model look like linkages with just compliant joints replaced in the traditional rigid mechanisms, right? So you can tell when something's been designed by topology optimization because it looks like a weird, organic, non-intuitive kind of mechanism. Whereas pseudo-rigid body model, it looks like a traditional, clean, nice linkage, the old school rigid mechanisms, except it's single piece with compliant hinges and these kind of joints instead of pin joints. And so you can just look at a mechanism and know what approach designed it. Okay, so it does kind of put you into a certain hole, or a certain type of mechanism you're going to generate depending on the approach you choose to generate it. So there's value in pursuing all these approaches because you can compare and see if you found a design that's the best. Oh, by the way, going back to topology optimization and pseudo-rigid body model is you can't ever know if you found the best design. In topology optimization, things optimize to the nearest local minima. Over the full design space, the goal would be to find the global minima, the point where the objective function, minimizes or maximizes, depending on how you set it up, right? But finds the global, the best over the full design space. You can never know if you found that. You could keep trying a bunch of different initial conditions and then see what local minima it optimizes to, and then compare those, and you can start knowing, well, okay, this local minima is better than that local minima. But then that becomes computationally expensive because you have to run it many, many times for many different initial conditions. And even then, you could do that forever, and you'll never know if you really found the global, unless you just stop generating any new designs after a very long time of doing it. And then you can have higher confidence you found the best design, right? But there's nothing that guides it to the best design, okay, for either of these approaches, really. If for a pseudo-rigid body model, you're just going to get a compliant analog to whatever mechanism you designed rigid, and who's to say that rigid mechanism is the best mechanism to do what you want? Okay, so these are other things to think about. Okay, so the third approach is constraint-based design, essentially. It's not nearly as systematic or rigorous a design approach. It's just kind of understanding principles of how things behave when they're constrained or not constrained, and then using your experience of that to kind of design stuff and constrain it so it moves the way you want with high compliance, but is constrained and restricted to move in other ways you don't want with high stiffness. And so there are some, this again, I think this is just kind of a, this is kind of an apprentice approach. You kind of need a lot of experience and you need a good mentor to kind of teach this to you. And then you just become a good constraint-based designer by knowing these principles, and you just then be creative and design stuff. So it's not a rigorous approach really at all, but it's completely different than topology optimization or pseudo-rigid body model. And it generates designs that kind of look like, rigid bodies with flexible elements stuck in it in 3D in interesting ways that are constraining things so they don't move in certain ways but allow things to move in other ways. So that's kind of what it is. I'm teaching these principles because they're very important principles and they're the foundation of the approach that I'm going to teach then for the rest of the course, which is the approach I created called Freedom And Constraint Topologies, which is very systematic, and it's really based off of the principles of constraint-based design. So this is very important. Okay, so now I'm going to start, from now till the rest of this lecture, we're going to talk about these principles of constraint-based design. Okay. Okay, so principle number 1 is that all 2D objects that are not constrained possess 3 degrees of freedom. Okay, 2 translations and 1 rotation. Okay, so you can know that if this, you've got some body, it's in 2 dimensions, that means it's stuck on the plane. It can really only translate in 2 directions, x and y, and then every combination of those, and a rotation in z, right? And every combination of those. Okay, so those are your 3 degrees of freedom for a planar system. The simplest constraint, flexible constraint, is a single wire flexure. And in 2D, it looks like this. It's grounded on one end. It's just this skinny little wire and attaches to something on the other end. So you could attach it to this block on this end here. And what it does is it's just it's a wire that basically just kills a single degree of freedom. And so what it does is you can notice here, of the 3 degrees of freedom, it kills the translation along its axis. You could imagine this is much stiffer. Excuse me. This is much stiffer along its axis. And by the way, you want to assume it doesn't really buckle. Okay, we're going to make some ideal constraint assumptions. Okay, but anyway, it's better to visualize. It's much stiffer in tension than it is in orthogonal direction and in bending, right? So what you would do is you'd model this in constraint-based design as an ideal constraint. You show them as blue lines that go through their axis. And the model is we're going to take gray out of reality and we're going to make it black and white. In other words, we're going to say this is infinitely stiff along this direction, both tension and compression. We don't allow this to buckle, and we don't allow it to stretch. It can't move, but it's infinitely compliant in perpendicular directions and in the bending rotation. Okay. Now, of course, that's not true, but it's a nice approximate model because, of course, there is a finite stiffness to this, and of course, this can buckle, and even when you pull it in tension, there's, like I said, a finite stiffness to it, and then these aren't infinitely compliant, the 2 existing degrees of freedom. They do have a stiffness associated with them, but it's reasonable because they're like an order of magnitude less stiffness. So they might as well. It's just in the context of constraint-based design, things are either constrained or they're not. So they're either impossible to move, they're infinitely stiff, fully constrained, you're done, or they're infinitely compliant and they can move with no resistance. Okay, so that's the model. Okay, and the other thing I want to mention here is you've probably gotten the idea that what degrees of freedom are in the context of compliant mechanisms. They're directions of high compliance. They're directions that the constraints aren't really constraining. So in other words, this motion and this motion aren't constrained by this wire, but this motion is. So that's what a degree of freedom is. They're directions that aren't constrained. Okay, whereas degrees of constraint are directions that are constrained with, and again, the model is infinite stiffness and these are infinite compliance. Okay. Now, in this lecture, I'm going to show you degrees of freedom with the compliant mechanisms actually deforming. So I will show this beam going up and down or rotating. And the reason I'm going to do that is because that's going to help your brain see that, oh yes, I can see those are directions of high compliance. Those constraints could deform those ways freely. And then you'll see that the animations I don't show are the ones that are obviously constrained. And that will help your brain recognize and convince you that these are directions of high compliance. But don't get confused with finite motions. I'm going to show them to show degrees of freedom, but degrees of freedom don't really have anything to do with finite motion. So, I said this one is a pure translation up. Well, you might say, well, but if you actually deform at a finite amount, it'll actually arc, because this beam will actually arc, and it's not a pure translation. Well, but that's the thing. Degrees of freedom have nothing to do with motions. They are directions of compliance. And if you do want to think of them as motions, think of them as infinitesimal increments of motion. So for the very first infinitesimal increment of motion, before this even really moves, it is a pure translation. Okay? And the other way to think about it is, I could give you a flexure stage and put it in front of you and ask you how many degrees of freedom does it have, and it doesn't have to move for you to tell me how many degrees of freedom it has. It has as many degrees